Welcome back. When we think of silicon in the context of microfabrication, microelectromechanical systems, MEMS, and semiconductor manufacturing, we often treat it as a singular entity. But from a materials science and engineering perspective, silicon is not just one material. It actually comes in three distinct structural forms: single crystal silicon, polycrystalline silicon, and amorphous silicon. The fundamental difference between these three states lies not in their chemical composition, they are all pure silicon, but in their crystallographic order. How are the atoms arranged across space? The answer to that question dictates everything from their electrical conductivity and mechanical stiffness to how they behave when etched by chemicals during fabrication. Today, we are going to break down the physics, the atomic structures, and the fabrication methodologies behind these three essential pillars of microelectronics. Let us begin with the gold standard of semiconductor substrates: single crystal silicon. In a single crystal material, the crystal lattice is completely regular and perfectly organized throughout the entire bulk of the material. There are no interruptions, no structural discontinuities, and no defects in the macroscopic order. If you know the orientation of the atoms in one corner of a 300 millimeter wafer, you know the orientation of the atoms on the exact opposite side. In microfabrication, you will typically encounter single crystal silicon in three primary scenarios. 1. Czochralski grown wafers. This is the classic approach, where a single crystal ingot is pulled and grown from a high-temperature melt, then sliced into the pristine wafers that serve as your mechanical handle and electronic substrate. 2. Epitaxial thin films. Here, we grow a single crystal layer directly on top of an existing substrate, atomic layer by atomic layer, maintaining perfect lattice continuity. 3. Recrystallized silicon. This occurs when we take polycrystalline or amorphous silicon and subject it to global or highly localized thermal treatment, such as laser annealing, to force the disordered atoms to recrystallize into a singular, continuous lattice. Because single crystal silicon lacks internal boundaries, it possesses highly predictable anisotropic properties. This means its mechanical behavior and chemical etch rates depend entirely on the crystallographic direction, whether you are cutting along the 100 or the 111 plane. But what happens when order is localized rather than global? This brings us to polycrystalline silicon, colloquially known in the clean room as polysilicon, poly-Si, or simply poly. As you can see in this schematic representation, polysilicon is composed of multiple crystalline domains, often called grains. Within any single domain, the crystal lattice is perfectly regular and aligned. However, the moment you move to a neighboring domain, the crystal orientation shifts. The boundaries where these differently oriented domains meet are called domain walls, or more commonly, grain boundaries. Do not underestimate these grain boundaries. They are highly chaotic, high-energy regions where the silicon atoms cannot satisfy their ideal bonding configurations. Consequently, grain boundaries play a massive, defining role in determining the material's macroscopic properties. They act as scattering centers for electrons, which significantly lowers electrical conductivity compared to single crystal silicon. They also alter the mechanical stiffness and drastically modify chemical etching characteristics, as etchants often attack grain boundaries much faster than the crystalline bulk. How do we create polysilicon? It is predominantly deposited via low-pressure chemical vapor deposition, or LPCVD, or by taking an amorphous film and utilizing thermal processing to induce nucleation and grain growth. Polysilicon is the workhorse material for gate electrodes in MOS transistors and structural layers in surface micromachined MEMS devices. Finally, we arrive at the third form, amorphous silicon. While single crystal silicon represents perfect global order, and polysilicon represents localized order, amorphous silicon exhibits no crystalline regularity whatsoever. The atoms are arranged in a highly disordered, quasi-random network, akin to a frozen liquid or glass. Why does this happen? It boils down to thermodynamics and kinetics during fabrication. Amorphous silicon films are typically deposited using chemical vapor deposition methods, but at much lower temperatures than those required for polysilicon. When the gaseous silicon precursors react and deposit atoms onto the substrate surface, the low temperature means the atoms simply do not possess enough thermal or vibrational energy to move around and find their thermodynamically preferred, highly ordered lattice positions. They are effectively frozen in place right where they land. In a typical horizontal, low-pressure reactor, there is a distinct transition temperature, generally hovering around 580 degrees Celsius. If you deposit above this threshold, you supply enough energy for a polycrystalline structure to form. Deposit below it, and you get an amorphous film. Furthermore, if we want to drop the temperature even lower to protect underlying layers, we can use plasma-enhanced chemical vapor deposition, which uses radio frequency energy rather than pure heat to drive the chemical reaction. So, why does the microfabrication engineer care about these three states? Because material structure dictates device application. You choose single crystal silicon when you need pristine electrical mobility for high-speed transistors, or highly predictable mechanical behavior for bulk micromachined sensors. You choose polysilicon when you need a compliant, conductive thin-film material that can be deposited conformally over complex, non-planar topography. And you choose amorphous silicon when your thermal budget is strictly limited, such as depositing active layers on top of low melting point glass or plastics for display technologies and solar photovoltaics. Understanding how to navigate, deposit, and manipulate these three structural states of silicon is one of the fundamental keys to mastering microfabrication process design. Thank you for joining today's lecture. In our next session, we will dive deeper into the kinetics of LPCVD reactors and model the transition phase between amorphous and crystalline kinetics. See you then, and please do not forget to subscribe to our channel.